Good evening, everyone. Welcome to the November meeting of the Naperville Astronomical Association from here in lovely, rainy northern Illinois. I'm Drew Carhart, the current club president. I'm going to find my little arrow here. There we go. Thanks for joining us. And as always, I want to remind everyone that this is a live program, at least what you're watching right now. And if you have any questions that you want to ask our speaker this evening, we have enabled that. All you need to do is, if you're on Facebook, put your questions in the comments section. And if you are not, or if you prefer to ask via email, we're also following our email account at questions@naperastro.org. And so anything you submit that way, Jim in our control room will be sorting through those, and he will present them to the speaker during the presentation. A couple of brief notes before the program starts. Once I get to go. So as announced in the club newsletter and by a special mailing that went out, I guess very early today, we do have some business that the members need to attend to. We need you to consider and vote on a couple of items. So at the close of the meeting today, we're going to shift the business portion to a Zoom meeting that will be open to all members. And we did distribute that information via the message board, but it was also published in the newsletter as the happy hour address, but this is the meeting ID. I will share it again before we head off there at the end of the program. But please do, members, please do join in there. It'll be a short business meeting, and it will then segue into the happy hour for anyone who wants to stay for that. I also wanted to note for everyone that you should visit us on our newly built up YouTube channel. All of the presentations that we've been doing since April pretty much have been edited and sorted out and put there. So they're available for review for things that you might have missed or that you would like to see all or parts of again. We have a terribly long randomly generated URL at the moment for our page, but if you go to YouTube and you search for the words Naperville and astronomy, I'm pretty sure we'll be at the top of the list. On the upcoming events list, we have our fundamentals program that is going to be just 1 week from tonight. It's normally 2 weeks after the regular meeting, but again, the regular meeting was delayed this month. So next week, Tuesday, the fundamentals program is on the topic of asteroids. So it's going to be a minor talk on minor bodies. No, that's not true. It'll be a very good talk. So that's fundamentals this month. Our December regular monthly meeting program on the 1st of December is going to be on the Great Telescope of Birr Castle. And if you don't know what that is, you should come and learn about it. It's been a little while since we've had a historical talk, and I guarantee this one will be interesting. Our calendar on our website will be kept up to date with these things. And what we can't always put on the calendar is the pop-up events, which we're still going to keep on trying to do when we do our observing days and evenings. When we've been live streaming, we can't put them on the calendar well in advance because we have to wait and see what the weather's going to be like. So oftentimes we'll only send out notice about them a day or so in advance. But follow us on Facebook or follow us on the club message board if you're members, and you can find out about them there. This evening we have a guest speaker, and he is Dr. James Ennis, and he is in the experimental astrophysics group at Fermilab. And I didn't even know how to title it. So it used to be called the LSST, and he's going to tell us, I'm sure, more about how it's been changing. Its various parts of it have been changing their names over the recent past. But without further ado, I'm going to turn the screen over to Jim. for tonight's presentation. So, Jim, you're welcome to take over. I'm going to stop sharing. And there we go.
So thank you for having me. This talk will be exotic by scientific standards. I want to say that when I go out at night, whether I'm at Fermilab or down at CTIO, where that picture is, and look up at the sky, I'm too busy watching stars and galaxies to worry about the animals around me. At Fermilab, we have bison and we have coyotes, and the physicists are strange too. At Blanco, we have not coyotes, they're actually foxes. And they come to visit us. But when I look at the sky, I'm struck by this feeling of distance and age and grandeur, much, much larger than me. And the Greeks, 2,000 years ago, thought similarly. We have writings from them. It's amazing we have writings 2,500 years old. Plato and Socrates, two of the most famous, to the Arab speakers and the Latin speakers that came after them, explicitly thought of the stars as divine, divinities. And Aristotle in particular thought of astronomy as experimental theology. It's strange when you read those texts. They're not modern humans. They're Greeks. They're not us. But there's a direct line of thought from Aristotle to us. I can read you some of them, and they just speak to the high-energy physicist in me. We think we know a thing when we know its first principles, its elements, and its origins. The most exact of sciences are those that deal with first principles. Science using fewer first principles are more exact. I was taught that in graduate school by my professors, that language. We want to derive things from first principles. My science is the astronomy of cosmology and the astronomy of large sky surveys. The next big leap forward in this big sky surveys is LSST, which is now named the Rubin Observatory, and it has a giant sky survey named the Legacy Survey of Space and Time, LSST. I'll mostly call it LSST. That's the survey for the next 10 years when it starts in a couple of years. At some level, it's going to be revolutionary because of the sheer size of the thing. This is on the edge of the Atacama in Chile at about 9,000 feet, 8,000 feet. And they're building a brand new telescope. They are constructing a brand new giant telescope. That's an 8.5-meter telescope. This is the primary mirror. Notice the exotic shape. It's not just one mirror, it's two optical elements in one. This is called the Simone Survey Telescope, the primary and the before. We're building a giant camera. It's about 0.5 meter across, has 3.2 gigapixels, has 189 CCDs. We just finished it a few months ago, maybe a few weeks ago, very recently. And this was from May 5th. We're not ready. We've been delayed about a year from the COVID-19 epidemic. But the sheer size of this thing is amazing. So it's going to take a picture every 20 seconds, every night for 10 years. If we get behind in the data taking, we're doomed. There's a large international federation of data facilities that will reduce the data, a combination of the US, France, and the United Kingdom. There's a 7+1 science collaborations already formed to deal with this data. They are the solar system, stars in the Milky Way, transients and variable stars, AGN and quasars, galaxies, strong lensing, and the one that I'm in, dark energy and cosmology. plus one that's a different kind of science, the science of statistics and large data sets. We're going to need all those people. Now, I am going to take a long diversion here. So astronomers are most, especially cosmologists, are most comfortable when speaking about 1,000,000 years. It's just what we do. A star, the shortest lived stars we know of last about 1,000,000 years. And yet when scientists give talks, what they'll usually do is give you the bleeding edge, all the stuff that happened in the last year, and don't give you any context. This entire talk is going to be context for the things I just told you, and why I think they are important, why I think there's revolutions in the making. When I wrote this, I was thinking of a deep time perspective. There's several threads we're going to follow. Some of them will be first principles related, like the distance. Some of them will be how the astronomers came by the money to do their projects. Some will be who were the astronomers. And one thread will be what does it mean to be a scientist and astronomer. So, as Aristotle said, that which is oldest is most honorable. He meant 200 years earlier, which is charming because he's 2,005 years, 100 years old to us. Let's start with Plato. There's a deeply influential and deeply strange book called Timaeus. If you read it, you'll recognize it all and think it's all foreign. Plato dreamed of the rational divine. He dreamed of it because he saw the sky rotating. And he thought you could study experimental theology by studying what we think of as sky rotation. His contemporary Eudoxus set out to mathematically predict the motions of the stars and the planets, and it set into motion a program that went through Ptolemy and Althussi and Chartier and Copernicus and Kepler, and ended in Newton, ways to predict the planet's orbits. I'm not going to follow that thread. You've heard that one before. You probably haven't heard this version of the story. We're going to follow a thread that's more like starting with Anaximander, who amounts to, in the Greek tradition, the inventor of space as opposed to a celestial sphere. He wanted to know how far away planets were. He guessed, he was wrong, but that's not too surprising. It was 500 BC. I do want to say one thing, universe. It seems so contemporary and scientific. It's Latin, universe. It comes from single rotation. That's what the Greeks thought of as the sky, the heavens, the world was the sky turning. So progress was made a century after Plato, in around 250 BC. It was very different times than the early Greek city-states. This was the time of the huge empires. There were several of them, and they ruled Egypt and Persia. Handfuls of Greeks ruled Egypt and Persia and Asia Minor, like Lydia, and actually the Greeks and the Macedonians, and they warred with each other. It wasn't too different than 1700s Europe, really, except that they were small numbers of Greeks and not nation states. So for the Greeks, they had this issue of what does it mean to be Greek when you grew up, you spent your whole life on the Nile, and you were born on the Nile. Are you Egyptian? Well, you're Greek. Well, what does that mean? Well, that means you speak Greek, and it means you think like an Athenian. But they had to demonstrate that, especially the rulers. I'm going to focus on the Egyptian Ptolemies. They're essentially pharaohs, but they're Greek pharaohs. And they had to establish that they were Greek to themselves and rulers to the people. So they established the museum at Alexandria, and the library of Alexandria. And this started into place, it's cemented in place, the system where scientists could flow around from empire to empire, from kingdom to kingdom, working wherever the money was. For instance, the person who helped set up the museum is a guy named Strato. He was not from Egypt. He wasn't even from Greece proper. He was from the Asia Minor. but he flowed to where his reputation preceded him, and he flowed to where the money was. Now in Alexandria, in the museum, the Ptolemy, the king, put a lot of money into it for a reason I'll get to a little bit later. But that money supported scientists. Euclid worked there. Euclid probably wasn't a person. Euclid was probably a team of mathematicians, like Bourbaki in early 21st century France, a team of French mathematicians who write books that are very conservative and very good. And if you've ever read Euclid's Elements, it's very good and very conservative, and there's nothing in it but geometry. Now, the Greek tradition for science is geometry. So I'm going to have to remind ourselves of a little bit of geometry, just a little bit. This is a right triangle. The magic in the right triangle, that is if you know an angle besides the right triangle, say theta, and you know one of the other sides, then you know everything about the triangle. You know all three sizes of the triangle. You know all three angles. That's simple. For cosine theta in particular, you take the hypotenuse and use it to divide by the adjacent length. And that gives you cosine theta. Or if you want to know what x is, you take y, multiply by cosine theta. The other piece of magic, this is more astronomy. This is deep astronomy magic, by the way. Like, I probably shouldn't tell you this if you don't have a PhD. But this is all astronomers probably from Euclid's time to now know this inside and out, use it all the time. So sine theta is the opposite of cosine theta. It's the opposite distance divided by the hypotenuse. So I call that L over D. L would be a length, and D would be a distance. And for small angles, theta much less than 1, sine of theta is about theta. So theta is equal to the size of an object divided by its distance. That's in radian, but you convert it to degrees. And that's magic. For everything in the sky that we care about, even the moon, theta is much less than 1. And you don't have to do geometry. You can just say theta is equal to L over D. And that's that. There's magic in that. For one thing, the Greeks, by the time of the Library of Alexandria, the Museum of Alexandria, knew that the eclipse, total solar eclipse is caused by the sun passing in front of the moon. They're the same size. That's what the eclipse is. If they're the same size, then the ratio of the size of the moon to the distance of the moon is the same as that ratio for the sun, which is dramatically cool, actually. So all you need to know is something about one of those distances, and you start learning about all the sizes, all the lengths. Okay, now let's talk about the first astronomer in my thread of history, which would be Aristarchus. We have one book from Aristarchus. It got put into a compendium of simple astronomy books. But since it's a compendium of elementary astronomy, it was widely copied. This manuscript is the earliest one known, the best copy known. It's from 950 AD. It's currently in the Vatican Library. It probably came from Constantinople. What you can see is the manuscript in the block and a whole bunch of commentary around the manuscript in the margins. That's where they put, and you can see a diagram. That's a 2,500-year-old diagram of astronomy. The circle on the left is the sun, the circle in the middle is the earth, and the thing on the right is the moon, and he's working through a lunar eclipse. And the thing about a lunar eclipse is that you can use it to get the distance to the moon in units of the Earth radius. And it's pretty straightforward. The length of time of lunar eclipse, the longest one that you know of, gives you the fraction of the lunar month that the Earth's shadow has. So if the Earth's shadow is exactly the same size as the Earth, then you know the size of the Earth in units of lunar orbit circumference or the lunar orbit distance. Now, the idea, in fact, that the shadow is not a same size as the Earth, but is smaller by some amount, was what Aristotle was working his way through. He would place limits on the size of the distance of the moon units the Earth with Euclidean style of very concrete mathematical geometric tricks. I mean, it's hard to read these days because no one thinks like Euclid. The last person who seriously studied it was 1901. The other thing that he noticed, he's more famous for this one. From the quarter moon, you know the geometry of the Earth, the moon, and the sun. It's a right triangle. If you know one side and you know one angle, you know everything about that triangle. So if you know that the moon gives you a right triangle, then all you have to do is measure the angle between the moon and the sun, and that gives you the distance of the sun units the distance of the moon, which is stunning and cool. And he was working through what the limit on that could possibly be. His size was, his size wasn't great. He knew it was big, but he didn't seem to have any observational capability. I'll get back to probably why he didn't have any observation capability. One thing is probably very young when he wrote that particular manuscript. But at this point, at around 275 BC, the professional astronomers working in the Eastern Mediterranean, in the complex of Pergamon and Rhodes and Samos and Athens and Alexandria and Syracuse on Sicily, knew about the size of the solar system. They knew it in terms of the size of the Earth. They knew the distance to the moon and the distance to the sun, all units of the size of the Earth. They didn't quite have a size of the Earth. These guys all knew it's spherical. They knew that 300-400 years earlier. They knew all about the geometry, but the Earth's size was a problem. So we'll go to our next guy, Eratosthenes, third head librarian of the Library of Alexandria. None of his books survive. I mean, that'll be a running theme. Most of the scientific and technical books from Eastern Mediterranean just didn't survive for 1,500 years. They got forgotten when the attention of the Mediterranean turned to how to improve the soul. Nobody wanted to spend the time or the effort to recopy these old tedious manuscripts. Yes, it's sort of worse than copying electromagnetics textbook. Why would you want to do that when you copy a novel? We have some fragments. Mostly what we have about Eratosthenes is popular science writing from a couple hundred years later. But we can piece together what he did. And the easy part, the astronomy part, goes like this. If you know a place on the Earth where on the summer solstice you put up a pole and it casts no shadow at noon, then if you walk due north by a long ways and do it again and measure length of the shadow, that gives you a triangle. I mean, you have the length of the pole, you have the length of the shadow, you know it's a right triangle, you know all the angles. One of those angles is the angle to the sun. So that's the astronomy part. You need to know the angle of the sun away from the zenith in this popular science version of this. The thing that you may or may not believe, but they're geometers, they would probably show this in great detail, is that same angle, this is from the zenith to the sun, is the angle of the Earth that you walked north. So as long as you know the distance you walked north, that angle gives you the fraction of the Earth you walked around. And if you know how long you walked, you can multiply it by the rest of the fraction of the Earth and get the Earth diameter. So what Eratosthenes did was take advantage of his position as the head librarian of Alexandria, probably tutor to the royal children, certainly with a lot of people and a lot of influence, to get his hands on the royal surveyors. The pharaohs, long centuries before this, had every year measured the distances to the changing Nile, almost certainly for tax collection purposes. These guys are nearly professional surveyors by this point. The real problem in measuring the size of the Earth is getting the geodesy right, getting the length of distance right. And Ptolemy's land in the direction of the Library of Alexandria made the measurement. They probably did many whole zenith angle measurements and several distance measurements and combined them in some clever way. We don't know. All we have is popular science account. He got it right to 2%. So in 250 BC, we knew the size of the Earth to, I don't know, 2%. He probably redefined this unit of length they had in terms of the Earth radius, just like we defined knots in that way. I'm sorry, did I say 2%? My notes here say 1%. It's hard to believe they were able to do that stuff, and yet that's the number that came down to us. So he was the head librarian of Alexandria. The whole game of science was not to make these measurements and keep it quiet, but to write it down and send it out to your colleagues. One of his correspondents, one of his contemporaries, was Archimedes, the mathematician. He worked in Syracuse on the island of Sicily, a very rich colony, had been for I don't know, centuries. Athens and the fall of Sparta foundered on an attempt to invade Syracuse. So Archimedes works of great sophistication, like really high levels of sophistication. He's a really great mathematician. Survived to this day by only a single manuscript. It fled Constantinople when Constantinople fell. It made its way to Italy just at the time that printing was being invented. This is a 1544 printing of that manuscript. And soon afterwards, the manuscript itself was lost. It was that close. The only reason it survived was 900 AD. Architects in Constantinople went to a high technical and scholarly phase, and they recopied all the old manuscripts. And they made a manuscript of Archimedes. But we can read them, still amazing. But we can't read the originals. All we can do is read the printed copies. Right, so about 8 books of Archimedes survived, one of which was a book called The Sand Reckoner. And The Sand Reckoner is this easy to read, amazing book where Archimedes takes the things that he talks about Aristarchus in this, he talks about Eratosthenes. He takes these measurements these people made and says, okay, well, we know the size of the solar system. He says all the way to the stars, the size of the solar system. And then he says, so How many grains of sand would it take to fill the solar system? Being Archimedes, he had to invent a whole new way to express large numbers in Greek. They didn't have that. He invented it. Just this thing, this document, this book was basically a show off to the king who funded him. It's amazing. It's an amazing book. We'll come back to that because it's actually interesting for many reasons, the sand reckoner. So who were these people? So, I mean, they're Greek mathematicians. Archimedes was the guy who ran Eureka, who said Eureka and ran naked through the streets of Syracuse. There's legends and there's books. But who are these guys? First of all, they're all guys. Near as I can tell, everyone in this thread from the Greek period were guys. Aristocles was from the island of Samos, which is one of the Ionian, kind of wealthy, not really. He was a student of Strato, who helped found the museum in Alexandria, but who himself was from a northern town halfway between Samos and Constantinople. After he worked at the museum setting it up with the Ptolemies, he went to Athens and ran Aristotle's old school for many years. So we think we have no information. Aristocles, we think, worked either in Athens or Alexandria, an example of the scientists flowing around the Mediterranean as Strato was. Archimedes was different. He was born and grew up in Syracuse. He probably went to Alexandria at some point. But Syracuse itself was wealthy enough that he just stayed there and worked. Eratosthenes is sort of interesting. He was born poor, but he was born in Cyrene and he came to maturity about the time that one of the Ptolemies married the queen from Cyrene, and she brought in a whole bunch of Cyrenians to Alexandria, including Eratosthenes, to help run the museum and the library. So he knew royalty. He was talented, surely. That's how he came to the attention of the royalty, but he knew royalty, as did Archimedes. Aristarchus didn't seem to. He probably didn't have any resources. Archimedes did, and Eratosthenes did. Why did they have resources? At this time, there was national prestige at stake and legitimacy, legitimization of rules of the museum and library, but also the way, we're way done with that. The way to conquer more cities in the Eastern Mediterranean was to use these giant ships. They were walled cities, they're all on the coast. You couldn't break down the walls unless you had catapults, so you need mathematicians and architects to build catapults. And then they had these giant ships that were catapult carriers, large, humongous, giant ships that were catapult carriers, wall destroyers, city destroyers. They would be surrounded by a fleet of smaller ships to go take on Rhodes, a super wealthy city, or Tyron, and Sidon, these super wealthy cities. So Ptolemy in particular is very strongly believed in this. So he had the scientists and mathematicians at the museum helping design these ships. Same with the king in Syracuse helping Archimedes design these ships and design the catapults. And there's legends about the weapons that Archimedes came up with for the king of Syracuse. What's pretty clear is Archimedes was killed when the Romans sacked Syracuse, and they took Syracuse. So it wasn't just a matter of national security, the life and death of some of these people. When the Romans took over, the funding sources went away and science ground to a near halt. These days, the best measurements to the moon use the retroreflectors the Apollo astronauts left. I think that's Apollo 14's retroreflectors there on the left. This is Apache Point. The photo in the lower right shows you two small telescopes. They end up being about 24 inches. An exotic looking telescope, which is 2.5 meter diameter. It's a Sloan telescope, Sloan Digital Sky Survey telescope. and a big telescope, a 3.5 meter. These are all modern. They're built in the 90s for the most part. Physicist astronomers will shine a bright laser up through the telescope using the telescope as a beam expander, shoot at the moon and get the photons back from the moon in 2.6 seconds. And that time it takes the photons to come back is the measurement of the distance to the moon. So our thread skips 1,000 years, 1,500 years. Lots of things are going on. The whole Althussi, Shatir, Copernicus, Kepler thread was going on. People are learning how to do the motions of the planets, but they weren't measuring distances. If they tried, they did things much worse than Aristophanes or Aristotle's. But astronomy had landed in this place where everything was relative. That made it possible to make progress. But what I mean by relative is that everything was relative to the distance of the sun, even the distance of the stars at some level. They invented this unit called the parsec. And I always found this really complicated when I was a student, but it's really, really simple. They said that, well, the distance of the sun, since distance to the sun is so long to say, we'll call it astronomical units because I don't know, we're astronomers. The distance to the sun, if you put it far enough away, remember L over D, if you put D big enough, then the distance to the sun, 1 AU, will be a small angle. How small an angle? I don't know, let's pick a round number. How about an arc second? So to remind you, a circle is 360 degrees. A degree is made up of 60 minutes. And each minute is made up of 60 seconds. Yes, it's time, but then that's what the Earth's rotation is. And yes, it's Babylonian. Believe it or not, Archimedes tried to make it round numbers of 10, but no one listened to him. If you put an astronomical unit far enough away, it'll subtend 1 arc second. How far away? Well, who knows? But we'll call that 1 parsec. So we don't know the size of an AU. We don't know the size of a parsec. If you divide the two, it'll be 1 arc second. That works really well, believe it or not. Still works really well. I still use parsecs. We use megaparsecs all the time, 1 million parsecs. For your edification, a parsec is pi light years, to fairly good accuracy, in fact. So it's pi light years. So the story picks up when the English astronomer Halley, around 1700, invented a way to measure the AUs, measure the distance to the sun. For the next 50 years, 2 French astronomers, guys named Delisle, like Lyle, Delisle, and Lalande, organized a very loose campaign to make this measurement. Where loose, I mean they sent letters. They had a letter writing campaign, but the letters were to the right people. They're the scientists in the Earth. The basic idea is actually really easy. It's just triangles again. If you're standing on the Earth and you look at the sun, now we're going to pretend that the Earth, the Venus, and the sun are all on a plane. They sort of are. We're going to pretend the Earth isn't tilted. Okay, fine. Then if you stand on the equator and look up at the Venus, you'll see it right in the middle of the disk of the sun at a very particular time when Venus is transiting the sun. But since Venus does transit the sun twice in a decade every 100, 200 years. And Halley realized that was coming up, and Delisle and Lalande realized that 1761 and 1769 there'd be 2 chances to measure the distance of the sun by parallax. So you just gotta stand at the equator, look up, measure where Venus is, and then go as far north as you can and look up and see where Venus is against the sun. It'll be a different place. Go far south as you can, know the latitude, look up and see where Venus is. Basically, Venus tracks across the sun in 3 separate trails. You could try to measure the distance from the equator of the sun to where the Venus went across, but that's hard. Instead, you could measure the time it takes Venus to go across the sun. That's pretty easy, it's just 6 o'clock. If you know the longitude of where you're standing on the Earth, as well as the latitude, then you just can measure the time when Venus touched the sun. And that works really well. And that's what they tried to do. What they what Delisle and Lalande did was make these maps. So I find this map fascinating. It's from 1761. Look down at Australia. These guys haven't finished mapping the Earth yet. They just don't know what's in the South Pacific. They haven't gone there. You know, people who live there know what's going on, but they don't know. And yet, if they could send people there, they can learn something about the size of the sun, the solar system. Excuse me a second. So the way to read these maps is that there's 3 different colors on there. Hard to tell. On the left is a green. That tells you where you can see the ingress. On the right is a yellow. That's where you can see the egress of Venus from the sun. And in the red, you can see both ingress and the egress of Venus hitting the sun. Remember, the game is to get as far north and as far south as possible. Now, the Earth is tilted, and they knew that. They had to calculate where you wanted to go. But logically, it was far north and far south as you could go. So they needed people everywhere. They needed people in Siberia. They needed people in India. They needed people in Africa. They needed people in Tahiti. Fortunately, they discovered Tahiti relatively recently. And so the story is, how did they get people to do that? This is the 1760 when they were 1758 when they were actually really trying to organize this. So what that meant was Lalande in particular, after Delisle died, Lalande took over, sent letters to the scientists in the great capitals of Europe, Paris, London, Berlin, St. Petersburg, Denmark, and Sweden. The scientists had already self-organized into the academies of science in each of those capitals. After all, this is the Enlightenment. Science had high reputation at that point. They had no money. They were just groupings of people. They're clubs, astronomy clubs. They were just people. They had no money. Let me say that again. They had no money. I mean, they were aristocrats. They had some money, but they didn't have a funding source, really. But they did, because they were royal academies, have an ear to the king. So they debated, planned, figured out where they wanted to send people, figured out who they could send. And then they went to their kings and asked for money. And various kings said yes, and various kings said no. Portugal and Spain wanted nothing to do with it. Most other people did in various ways, in forms. France was sort of the intellectual center of it, kind of. England probably spent more money on it. I mean, various amounts of success. In the 1761 transit, there were 70 observations around the world. The British formed the Mason-Dixon team for the first time and sent it to South Africa. Later, they'd go on to measure the Mason-Dixon line, and famous in US history. They went because there was money. They were paid. I mean, that's why they gave them something to do for 2 years. The French sent a totally unsuitable guy, an astronomer, to Siberia to make the measurement. The Russians did their observations in St. Petersburg. The British colonials that lived on the East Coast, went up to Newfoundland to make observations. They did a fair job in the first one, but they knew that was really a training exercise for the second one. The second one, they had better clocks, which you need. They had better telescopes, which they sort of had at that point. And they were better organized. So like they actually convinced the King of England to give them a ship, and they sent Captain Cook to the South Pacific to make the measurements of transit of Venus in 1769. He, quote, discovered the Great Barrier Reef on those trips. There were a nobleman with them and some other scientists. But I mean, the French sent that same unsuitable guy who went to Siberia. He was really good observer. They sent him to Baja California with an expedition. The entire expedition died but one guy, but they died after they made the great observations of the transit. They were really good observations. The Americans did their part. 70 different observations in the second transit. They measured the size of the solar system. Now, there was no funding for the data reduction. That was a problem because the clocks weren't that accurate. People didn't know longitude as well as they thought they did. Sometimes the observers just messed up. And they discovered that Venus had an atmosphere, which kind of messed up the measurements. They still could do it, but various people made runs at it. There were lots of arguments. A handful got really nice measurements just by having data takes and knowing which observations to believe. They argued for about 30, 40 more years about those measurements. What I think was a great success was this international effort of the astronomers and scientists going all over the world to make these measurements. So who were the scientists? Mostly men. There's records of one mathematician who was female in France, but the records have mostly been erased. There was a revolution a couple of years later, a lot of records were destroyed. There's not a lot of evidence of anyone else. It's clear they didn't send letters to the Ottoman Empire. It just didn't occur to them, nor to the Chinese. So it was all Europeans. But they got money to send observers all over the globe to measure the size of the solar system. It was really cool. In 1961, the Americans needed to know the size of the system to very high accuracy in order to do interplanetary navigation. They built a radio telescope called Goldstone in the California deserts. And they sent a radar pulse off to Venus, measured the round trip time. It took 6.5 minutes, and that yielded a 0.2% measurement of the AU. Clearly, the preferred method these days is to use the speed of light to make distance measurements. Okay, we're back to the Archimedes, the sand reckoner. Why am I back to Archimedes? Because I argue that we lost most of the records from that Hellenistic period. We just did. We did get the sand reckoner. It survived barely to us. In the sand reckoner, Archimedes is talking about Aristarchus, sort of throwaway sentences. And he says that Aristarchus had a heliocentric solar system, which is remarkable. He liked it better. As far as we know, only one scientist followed Aristarchus in this. He was a Babylonian astronomer, in the Greek Empire, but probably a Babylonian astronomer, and no one else did. And the question is, why not? I mean, to us, it's, the sun's the center of the solar system. We know that. It just works. Why didn't those Greeks? Well, my argument is they tried the measurement and failed. So what measurement would they have tried? This one, parallax, where you use the Earth revolution around the sun as a platform to watch a star move against the background stars. So on one side of the sun, you see the star against background stars in one position. Wait 6 months, make the same measurement, and see it on the other side. That's very simple geometry. That one is a sine data measurement, but okay. The Greeks are perfectly capable of knowing this argument and writing it down and trying it. What they weren't capable of is making the measurement. They almost certainly tried and didn't see anything. The human eye can see 1 arc minute. That's 20/20 vision. It's about an arc minute. 1 arc minute of parallax is what you get when an object, try this again. 1 arc minute of parallax is what you get when an object is at the distance of 80 light hours, and Neptune is at 4 light hours. If they'd known about Neptune, they might have been able to do it and move slowly enough, but they didn't. They couldn't see Neptune, nor could they see 1 arc second scale parallax measure. I think the professional astronomers in the Eastern Mediterranean made this measurement and saw nothing and decided, well, Aristarchus is wrong. I mean, it's not crazy. I mean, the telescope was invented in 1600. In 1800, 200 years later, they still hadn't measured parallax. People routinely and always underestimate the size of the distance of the stars. They're really far away, and it's just not the kind of ratios to the solar distance that people can comprehend. So it had to wait until optics, of all things, optics of all things had supported the measurement. So our thread moves to, of all places, the Prussian Empire or Prussia Kingdom, depending on what authority I read. We're talking about 1820 or so. Napoleon's been defeated, but the story started with right around Napoleon trying to take over Europe. A guy named Bessel, I know him as a mathematician. Bessel functions are central to my cosmology. A guy named Bessel ended up as a head of an observatory in a part of Prussia that is now Russia. He had a certain budget associated with the university. At this period of time, most funding came through universities. So the royalty probably supported, the state supported the universities, and money flowed out from universities to people like Bessel in his observatory. He farmed out telescope making to a guy named Fraunhofer in the Kingdom of Bavaria, a separate kingdom. The guy in Bavaria was making a career, and was sort of brilliant, actually, of making better and better optics. He made beautiful telescopes, like world class, the best in the world. He kept on improving them. Fraunhofer designed this kind of telescope that would put two pictures of the same field of view onto the human eye, which you would think would be not useful, except that one of the images they could move around by a little vernier screw. And so you could measure distances on angles in the sky, small angles in the sky, by moving the vernier screw until two star images overlapped, and then seeing how much the vernier screw moved. That was your measurement of the angle. I mean, it was sophisticated, but it sort of wasn't. It was a brick building in Prussia with a dome on top. I mean, there are domes now, fine. It was a wooden telescope, not very big, but sophisticated optics that Fraunhofer gave to Bessel. So really, it was a collaboration between Bessel and Fraunhofer that made this work. Bessel used that for a couple of years. He had to choose what star to look at. A few years earlier, it had been noticed that a particular star called 61 Cygni was moving very fast from the sky. Bessel guessed that that meant it was close and aimed his instrument at that for several years. He was able to measure the parallax. It was 0.3 arc seconds in 1837. He measured it to 0.3 arc seconds. It turns out that 61 Cygni is at about 10.5 light years. You actually know that from parallax measurement, by the way. It's a direct geometrical measurement of distance and is the premier world-class way to measure distance to the stars, is parallax. The closest star we know of is Alpha Centauri, or Proxima Centauri. It's at 4 light years. 61 Cygni is very close. To give you an idea, like, it's not that other people hadn't tried. Around 1727, astronomer noticed the aberration due to Earth velocity. So Earth going around the sun is an Earth velocity vector. And the velocity vector in one direction causes the stars to move, and the other direction moves the other way. It looks just like parallax, except that it's a whole season out of phase. You can just prove it's not parallax. They were able to measure that because it was kind of big. So they saw aberration due to Earth velocity 100 years before they saw parallax. Parallax is really small. The distance of stars is very large. I mean, it's worth noting that they measured parallax only a couple decades before they ended slavery in the US. It's modern. It's relatively modern. It's modern. Like in 2013, the European Space Agency launched the Gaia spacecraft. That's the spacecraft on the right. On the left is a giant camera. I mean, I was aghast. They were building this in the 2000s. We were using a Sloan camera to map the sky, and they were talking about launching a Sloan camera into orbit. I was horrified. They did a great job. That satellite on the right, you're looking at those two windows. When they wire the windows, those are where the mirrors are. They're going to project two different images of the sky, 106 degrees apart, onto that CCD focal plane and measure the star positions. This thing measures parallax just like everything else does as Earth goes around the sun. But it's able to measure parallax all the way to the galactic center. It's going to measure half the stars in the galaxy, the distances to them. It's a spectacular instrument. We're still using parallax. Parallax is the way to make distance measurements in astronomy. If you can measure it, you want to use parallax. There are no systematic errors. There are, but they're modern systematic errors. So who were these guys? Well, try to remember who they were. Fraunhofer was Fraunhofer and Bessel. So Fraunhofer was an orphan, apprenticed to kind of an evil glassmaker whose building collapsed, killing the glassmaker. But a prince, of all things, a prince elector of Munich? Bavaria, was there when they were trying to rescue the kid. When the kid came out alive, the prince took a liking to him and started funding his education, let him read books, where the prince's master didn't. He used some of that money to become an apprentice to another glassmaker. Eventually, he went to a brand new glassmaking endeavor. It's hard to call it a business. They made it into a business where he revolutionized glass making. He was lucky. He was a smart guy. He was lucky that there was a prince around and he didn't die. And he was lucky. Bessel was involved in shipping and learned navigation. He did this comet orbit that caught the attention of a famous astronomer who kind of introduced him to the king. The king needed someone to run an observatory that he was building. And so they assigned this 25-year-old to do it. He too was smart. So random people, random events, I mean, neither of them went to university. Random events got them in a position to do brilliantly. But not everyone gets random events. Why isn't this a better known story? Why isn't Bessel and Fraunhofer better known? One probable reason is that no one really wants to talk about where they did their work. It's a part of Prussia, which was the ringleader in World War I, later in the German Union. That part of Prussia became Russia after World War II. During World War II, the Americans bombed that observatory into oblivion. There's nothing left of it. Probably the instrument survived. That first measured parallax until, I guess it was the British technically, bombed the observatory. It's now part of Russia. It's called Kaliningrad. Neither side particularly wants to bring up that it was not quite German 100 years earlier, 200 years earlier. But life goes on. I've got to shift a gear a little bit because you have to know a little bit about the following. Quantum mechanics. So that picture on the left is a picture of what you get when you heat up hydrogen and let it glow and run it through a spectrograph. A spectrograph, by the way, that Fraunhofer invented. And it's not a continuous smear of light. They come out in lines. There's a mathematician who is alive now but was most productive in 1990s named Elaine Connes that described this as non-commuting geometry. And he says you can just look at those lines and know that quantum mechanics has to be non-commuting. The point is that you can look at this and see that quantum mechanics must exist. But those patterns makes it really easy to measure what I'm going to talk about next, which is a guy named Slipher, who grew up in Indiana, not too far from here, and went to work at the Lowell Observatory. Lowell was I don't know how he made his money, but he was rich. And he spent what would now be around $100 million to build the Lowell Observatory and outfit it with a staff of astronomers like Lowell and like Slipher, and to build a world-class instrument, which would be this refractor on the left. Remember, those are lenses. It amounts to a 24-inch telescope, same as the small ones we saw at Apache Point. Slipher ordered a spectrograph, which is the thing in the middle. It was a fast spectrograph, a technical kind of spectrograph that made it possible to measure low signal brightness things. He used it for a long time to measure star velocities. After all, you know the lines, and you measure them away from where they are from a gas lamp in the observatory itself. You know something must be moving. Since it's not you, it must be the stars. You get a velocity. But around 1917, he turned on to spiral nebulae and measured high velocities, either negative or positive, mostly positive. So we sort of knew redshift existed before we knew the spiral nebulae were galaxies. So in 1917, he published 25 spiral nebulae, a heroic achievement. No one else was measuring spiral nebulae velocities. 25, mind you. A little later, Hubble came. Also, he grew up in Wheaton, or he basically grew up in Wheaton. After going to England, he became a staff astronomer at the Wilson Observatory. The Wilson Observatory was a, I don't know, $775 million endeavor. They had one of the first reflector telescopes, mirrors. The thing on the right is the famous Hooker telescope, where Hubble worked. It's 100 inches, called the 100-inch Hooker. So that's 2.5 meters in modern language. So the 2.5 meter that Hubble used to establish that the galaxies were galaxies, spiral nebulae were galaxies, they're far away. Mostly they looked at the biggest one, M31, Andromeda Galaxy, and saw Cepheus in them. So real astronomy. But he established that there's a distance redshift relation. And so the rest of what I'm going to talk about is establishing the distance redshift relation. Hubble thought was linear up to errors and systematics. It is linear up to a certain distance, but no farther. So who were those two guys? They both went to university. And then they got luck. So were women allowed in university? Yeah, sort of. In Harvard at that time, they were allowed to be calculators. But they weren't really allowed to be scientists. So some great science came out of Harvard by the Harvard calculators. But mostly it was men out doing things because 1900s. And they got picked up by private donors who wanted to run world-class observatories. So they worked at private companies, but they weren't really like now there were nonprofits. Like Hubble worked at the Carnegie Institute of Pasadena, and Slipher worked for the Lowell Observatory. Remember, Lowell spent something like $100 million. Whoever built the Mount Wilson spent more like $775 million. Large in modern 2015 dollars. And they had a staff of astronomers who were the only ones with access to those telescopes. So these people were very, very good astronomers with exclusive access to world-class instruments, and they made great progress with them. Okay, World War II. World War II was a turning point to the way the US, at least, funded science. In a large part, that was because of Vannevar Bush's The Endless Frontier. Just a report he gave to the President of the United States. It's very thin. In it, he argued that national defense and national health, the health of the armies, required science, and that the federal government should heavily invest in science, regardless of the wealth of the people trying to do the science, in order to make the best possible science for the US. That worked. The US established the National Science Foundation, which funds proposals that come in on a competitive basis. A direct result of the Manhattan Project was the entities that became the Department of Energy, and it evolved to handle all large-scale high-energy physics projects in the US. So the Department of Energy and National Science Foundation will figure in to the rest of my story. And around 1960, 65, the astronomers got together and proposed to the National Science Foundation to build telescopes on Kitt Peak that would be a national observatory, an open skies observatory. Anyone could write a proposal to use them. And anyone in the world can write a proposal to use these telescopes. And in a competitive process, they'll be chosen. They built a 4-meter telescope, much bigger at Kitt Peak, which is a beautiful telescope. They built a 4-meter telescope in Tololo on the edge of the Atacama called the Blanco, another beautiful telescope. The 60s, 70s era technology, the battleships. They were made to carry people to prime focus. They're great engineering. But one of the revolutions was this open sky. They didn't provide money, but they provide access to world-class instruments, anyone who could write a proposal. That was a revolution in itself. So now we're ready for the 21st century. And getting close to the Rubin. But you're now ready to understand the Rubin. And that's because we're ready to talk about the Sloan Digital Sky Survey. All 3 other projects we're going to talk about, including the Rubin's LSST, descended from the Sloan Digital Sky Survey directly. The same people did these projects, line of sight. This is a picture of the instrumentation. That exotic telescope is a 2.5-meter Sloan telescope at Apache Point. It's a wide field special purpose telescope with large optics, 2.5-meter optics, but large corrector optics. We built the world's largest camera at the time, which is in the top middle photograph, in which you can see different filters glued into place on top of the camera. We built a 600 fiber spectrograph. That means every time we take a picture of the sky, we can get 600 redshifts, but we had to plug the plates by hand, which is what she's doing there. And we had to have a different plate every time we point to the telescope. The picture on the right shows the back of the telescope. I mean, this is real science in action. Notice the cardboard box around the computer, laptop, real science. And Connie there on the left in the red and the maroon t-shirt, she's from the University of Chicago. That laptop controls the telescope. It's the very highest of tech and the very lowest of tech combined to do this stuff. The green is the spectrographs. The black in the back on the right picture is the camera. We would take the camera off and put in the plug plate to do spectroscopy. We had people doing that because it was the cheapest thing we could do. Okay, why is this revolutionary? First of all, the collaboration was big, 100 to 200 physicists, astronomers. It was, hundreds of physicists were used to that, but astronomers were aghast. They're used to 3, 4 member collaborations. Second, the collaboration members are intimately involved in building less the telescope, but building the telescope, more the camera, more the spectrographs, and doing the software and then analyzing the data. For basically from Mount Wilson through the national observatories, there was this great divide between the instrument builders and the scientists doing the use of them, the observers. Jim Gunn, one of the leaders of the Sloan, really wanted to combine them back and have the scientists be the same people who built the instrument that used the instrument. and he succeeded at that. Lastly, the 600 fiber spectrograph was the point. We wanted to get 1 million redshifts, but we didn't have a good map of the northern sky to collect the galaxies, decide which galaxies we're going to get redshifts from. So we used this big camera to image the entire northern sky, 10,000 square degrees, a quarter of the sky. Lastly, the funding for this. It's called the Sloan Digital Sky Survey. This is the Sloan Foundation put in early money, a large amount of early money to buy the mirror for the telescope. The universities, there's a consortium of universities, put up a lot of money to get it going. Without the National Science Foundation large grant, we never would have begun operations. And the single biggest funder was probably the Department of Energy's Office of Science for staff scientists at Fermilab to operate the thing and to reduce the data. It was a multi-pronged funding model that works because no one entity puts up all the money. And it's what we've been doing for 20 years now, 25 years now. It's exotic by all prior standards, and it works great. So what also is revolutionary about this? The 1 million galaxies let us do this. It let us measure the baryonic acoustic oscillations. So the map on the left is Planck whole sky CMB map, CMB fluctuations. The map in the right, the big one, is a particular projection, which is what the Earth is supposed to show you. The map on the right is the galaxy distribution, not from the Sloan, because it only covered half the sky, but a much shallower survey called 2MASS, infrared galaxies. And you'll see patterns in the CMB. You'll see patterns in the galaxy distribution. It's a whole different lecture to tell you what the CMB fluctuations mean. I'm happy to do that lecture, but it's not this lecture. But if you do a Fourier transform of those fluctuations, you can just see that the bulk of the power is on 1 degree scales. So 1 degree scales are special in that map. If you do the similar thing in the map on the right, you also find 1 degree, but you have to do a lot more work. That map in itself can't do it. The Sloan 3D map can do it. That alone tells you that you can measure relative distances to the microwave background. That's all. I mean, it's the same, I believe, and there's reason to believe this. These are the same features, one, the microwave background, and then later, after fluctuations grow into galaxies, in the galaxies. And since theta is L over D, if theta is the same, well, you can measure the relative distances by the relative sizes of the angle. But it's more than that, because the CMB fluctuations you can derive from first principles. It takes many first principles, but you can derive them from first principles. We know the size of the fluctuations in megaparsecs, not 100 megaparsecs. And we can measure the angle in the CMB. So that's calibrated. We know the distance to the CMB very well, actually, like very well, actually. With the baryonic acoustic oscillations that Sloan Digital Sky Survey discovered, we can measure distance to every redshift that we can measure there in acoustic oscillators. I'll call them BAOs in that one. The Sloan could measure the BAO feature at about redshift a third, at 0.4. And so therefore we know the distance to the redshift at redshift 0.4. And cosmology now lives in the relationship between distance and redshift, because redshift is so easy to measure. Like we use it for a proxy for redshift. We also use it for a proxy for time, and we use it for a proxy for distance. But if we know the mapping between distance and redshift, we know the cosmology. That is the cosmology. So that was a breakthrough. It really was. Sloan did it. So we're following that up, of course, in the next project. This one, now I'm going to go fast over the next two before I hit the ribbon again. This is called the Dark Energy Spectroscopic Instrument, but no one calls it that. Everyone calls it DESI. That telescope on the left is the Mayall that was built in the 60s and 70s by the NSF-funded project to have open skies. Now it's a medium scale telescope. After all, 4 meter, which is what it is, about the same size as that 3.5 meter I showed at Apache Point. But we're going to build this giant spectrograph at the prime focus. The spectrograph is going to have 5,000 fibers. Instead of hand plugging plates, we have little robots move fibers around. This little up in the upper right is little robot arms. Now they can't move them far. Mostly they can move them in a circle, but they can move it. They can patrol a circle and lay a fiber down exactly where a galaxy would be. The lower right shows you all 5,000 fibers on the focal plane. We bolt that focal plane up at the prime focus, and we take 5,000 spectra at a time. We want to measure the baryon acoustical oscillation at every redshift from 0 through, actually more like 0.2. Redshift 0.2 to redshift 2.5. It's a great experiment. It would have started already, but COVID's a problem, so we haven't. But it's going to start any day now. The other project, which just finished observing about a year ago, was the DES, and that was a big giant camera. So notice the DESI was pursuing the spectroscopic part of this SDSS. It's actually the same people who did spectroscopic survey at SDSS decided to build DESI after the SDSS, or contemporary with SDSS. It's sort of ongoing for some other projects. Some of the same people, the SDSS went to build a giant camera, this one, DECam. It's 60 CCDs on a big focal plane. It is mounted to the Blanco telescope that looks just like the one in the north, but in the south in the Atacama. And we measured an imaging survey, did the imaging survey deeper because of the bigger telescope in the south, and measured things like weak lensing. The weak lensing is here as an equation, sorry, is part of a program to map the cosmology. And really the mapping is the top equation. If the photon travels from redshift z to us, you know its distance by doing the integral of the expansion rate of the universe all the way to us, redshift 0. So you have to integrate 1 over hz, hz being the expansion rate of the universe. But the Friedmann equation of general relativity tells you how to do that. So you know what the expansion rate is. Expansion rate is the second equation, which looks horrible. But really, omega is a number between 0 and 1, and it's the fraction of the universe that's held in a particular kind of entity. Omega r is a fraction in radiation, which is small. Omega dm is a fraction in dark matter, which is large. Omega m is a fraction in normal matter, which is kind of small. Omega k is amount in space-time curvature, global curvature, which is small but non-zero currently. And omega lambda is the cosmological constant. So look at those 1 plus z's. What that means is those omega r's at 0 redshift, and you know how they evolve with redshift. Radiation goes to z to the 4th, matter z to 3rd, so that's just the volume of the universe is getting bigger, and therefore matter is less dense. Curvature goes to squared, fine. And the curvature doesn't change, and the cosmological constant doesn't change at all. 1 plus z to 0. That is why it's a constant, cosmological constant. What we're up to is trying to measure those parameters, omega r, omega dm, omega m, omega k, and omega lambda, in order to do the cosmology, do the mapping. Which brings us all the way back to the Rubin Observatory. The Rubin Observatory is also descendant from the SDSS. Some of the same people at the SDSS are ringleading the Rubin Observatory. It was the LSST that renamed it after Vera Rubin, we'll get to at the very end. It's a brand new observatory in the Atacama near Cerro Tololo, where we did the dark energy survey. We're almost done building the telescope. The telescope is a special purpose 8.5 meter wide field telescope with an exotic primary. It's named the Simone telescope, Simone survey telescope. These are just some of the people involved in the construction project. The Simone telescope because Charles Simone and Lisa Simone, along with Bill Gates, private funding, gave us a large amount of money early to buy the primary and get it polished into its very exotic shape. It's called the SLAC LSST camera because the Department of Energy is paying for the construction of the camera. It's about 1/3 of the total NSF cost. It's very expensive, it's very complicated, and DOE is paying for it. SLAC is the national lab that built it. It's called the SLAC LSST camera. There are the NSF, who's doing the observatory, is paying for the observatory and the data management system. And the NSF is going to run half operations. So their half is funded by Department of Energy's Office of Science to run a data facility to reduce the data that involves data facilities in the US, in France, and England. But there are scientists from all over the world, 6 continents, that are involved with this project. They all have access to the data. Not everyone, you have to buy in particular ways. And we have 7+1 science collaborations to analyze the data. So this is a picture of the dark energy science collaboration. That's maybe a third of the people. I mean, they're just people, but they're some of the world's best scientists. And we need them all. I mean, to me, they're my community. They're my friends. The lady in the red near the front on the right is Rachel Mandelbaum. And she's the head of the Dark Energy Survey Science Collaboration. Some of these other people I've known for 20, 25 years. The guy with the big smile in front is Eli. Of course he's standing in front. I know him. Of course he'd be standing in the front. We need all these people. I mean, they are the heart and soul. They're the ones that help build the telescope. They help build the data reduction. They help build the camera. And they are going to help analyze the data. And data is complicated. And we're going to need every single one of them. On the other hand, we can keep 1,500 people busy extracting science from this telescope. So at some level, it's a great national success that 1,500 scientists from all over the world want to come use a US telescope. And we'll keep them all busy. For me personally, I've gotten distracted because the LIGO Gravitational Observatory came online. And it turns out that every time it detects an object, it measures a first principles distance to it. Mostly because a pair of bowling balls orbiting each other is a very particularly easy system to model, even in general relativity. They get a distance. They basically don't know where it's in the sky, and they certainly don't know its redshift, which is why we use the Dark Energy Survey's DE-CAM to find the objects and get its redshift. So we're off trying to get redshifts for these gravitational wave events in order to measure the cosmology. The Rubin Observatory will too. DESI will when it gets online. Rubin will get online in 23, I think it looks like these days. It's science progresses, first principles measurements progresses, and Rubin will be a revolutionary part of it with its image of the sky every 3 nights. So lastly, I want to show you Vera. That's Vera Rubin. You'll probably notice how few females were in this talk. Vera was one of them. This picture is probably from the 60s, maybe the early 70s, I think 60s. I had a job interview with her when I was a young scientist. She was frankly more interested in listening about the recent discovery of planet on a pulsar than she was talking to me, but it was great. This is a picture that the LSST camera took of a picture of Vera. She's working on scanning plates of galaxies here. She like, if you don't know, she's the one that convinced the astronomy community that dark matter existed. She should have gotten the Nobel Prize, but for some reason in the late 20th century, we didn't give Nobel Prizes to female astronomers. But this is a real-time, I can give you the URL, interface to the LSST camera data. We'll make, when we get this on the telescope, we'll give you the same access to it. I mean, I get way down in here. I want to look at, I'm an astronomer. I want to see the details. That's dust on the lens, and it gives us a very particular pattern. I don't mind because I mostly want to see the little white dot next to the dust rings. That's a cosmic ray. That's a single pixel. I want to get in here and see the single pixels on this camera. And you can, and we're going to have these technologies to make everyone able to see it. We named after Vera because Vera Rubin was a spectacular 60s, 70s scientist. And we think she deserves to be honored in this fashion. So it's the Rubin Observatory, and it's the LSST, the Large Survey of Space and Time, using the Simone telescope at the National Optical Observatories. And so thank you very much for your time.
Were there any questions to pass along, Jim? Jim's there. Hello, Jim.
Sorry, I had to unmute. We had one that said, how long is it anticipated that it will take to complete the data reduction process once the survey has completed?
We want to get the data out quickly, so it will be a year. The first data release happens a year after we take the data. So that will be catalogs and images. It won't be the cosmology papers. The cosmology papers will take longer. But the first papers will start coming out as soon as we get the data out the door. We can't afford to get behind by 10 years. We can't afford to get behind by a year. The data will have to be reduced quickly.
Okay, that was the only question that we had that was related to your talk on Facebook.
Okay, well, thank you very much, Jim. You give people a lot to think about. I'm going to go back to, hopefully, this. So we're going to do a little bit unusual here. We normally would just hold our brief business meeting as part of this presentation, but since we have a few items for the members to discuss and vote on, we're going to stop this stream. And again, members, you should have gotten an email that has this meeting information in it. Otherwise, you've got a moment here to jot it down. I want to thank everybody who joined us and hope you enjoyed the program. Once again, watch it on our website. Look for the calendar at neighborastro.org for other upcoming events. And I think we're just going to go ahead and, Jim, we're going to cut out and end this stream. And members, once again, within a minute or two, we will have this Zoom meeting going for you to join in on for the business portion. So otherwise, to everybody else who's leaving us tonight, again, thanks a lot for joining us, and we'll see you the next time out. Good night.